Hello everyone, my name is Ivy Wu, and I'm going to talk about defeating graph analysis of anonymous transactions. This is a joint work with Christoph Egger, Russell Lai, Victoria Gronge, and Hoover Yin. Our work is about ring-based anonymous transactions. In a ring-based anonymous transaction, a user signs a transaction without revealing its identity. This is done by forming an ad hoc group with some other users and proving that the signer itself belongs to the group. For historical reason, this group is also called a ring, and those other users in the ring are called the decoys. In this case, the public only knows that the transaction is signed by one of the ring members, but they don't know who the actual signer is. Given this mechanism, a natural question would be how these rings should be sampled, which is the central focus of our work. To formalize this concept, in a previous work, Gronge et al. Introduced the notion of ring samplers. Let U be the set of all users. A ring sampler is a probabilistic polynomial time algorithm which inputs a signer I in U and outputs a ring R such that I is in R and R is a subset of U. We see that the real signer I is hidden within the ring R. Typically, for efficiency reasons, we want the ring size to be much smaller than the number of users. The authors further introduced a class of ring samplers called the partitioning samplers. A partitioning sampler would partition the set of all users into chunks, then sample some number k decoys uniformly randomly from the chunk that the signer belongs to. The authors showed that the partitioning samplers achieve near-optimal local anonymity, where local here refers to anonymity at any individual time. Moreover, a partitioning sampler has the advantage that it is simple to implement in practice. Given this background, we are therefore interested in further investigating the partitioning samplers. Specifically, we ask, what if we consider the global anonymity of ring samplers, where by global we mean the anonymity throughout time? For this, we define the graph-based anonymity of ring samplers. That is, how well can a ring sampler resist the anonymization attacks that are based on graph analyzing the ring memberships of all the transactions in the history. Next, with this global anonymity measure in mind, we further ask, what is the ring size that one should pick? We know that on the one hand, anonymity increases with the ring size, but on the other hand, efficiency decreases with the ring size. Therefore, we want to know what is a good middle ground, and this will be the question that we attempt to answer. To formalize our question, we define the notion of transaction graphs, which is a graph representation of the ring memberships of transactions. A transaction graph is a bipartite graph G represented by the tuple U, R, and E, where U is the set of users, R is the set of rings, and E is the set of edges representing ring memberships, where an edge ij means that user I is in ring J. On the right, I give an example transaction graph with 5 users and 3 rings, and for example, the edges 1, 1, and 2, 1 here means that users 1 and 2 are members of ring 1. In a transaction graph, there must exist at least one maximum matching, and without loss of generality, we can assume that all edges II are in the graph. As an example, here I have highlighted one maximum matching in red. The reason that there must exist a maximum matching is that a maximum matching here has the semantic meaning that it represents a possible signer-signature assignment. That is, for example, the maximum matching that is in red now says that user 1 is the real signer of ring 1 and user 2 is the real signer of ring 2 and so on. And now I'm showing another maximum matching, and this one says that user 2 is the real signer of ring 1 and so on. Now to model graph-based de-anonymization attacks, we introduce the following security gain. In the experiment here, GSAM inputs the set of users and the number of rings and outputs a transaction graph G together with a maximum matching M in G, which represents the true signer-signature assignment. Note that the randomness of the output graph G depends on the ring sampler that is used. Given the graph G, the adversary wins if it can output an edge in G which is also in M, that is, it guesses the real signer of a ring correctly. With this experiment, now our goal is to look for a ring size which can lead to a low winning probability for the adversary in this experiment, which also means a high anonymity for the users under graph-based attacks. So what can a graph analyzing adversary do with a transaction graph G? To answer this, we consider the DM decomposition, which decomposes G into two parts. The first part is called the core of G equals UR E prime, which is a subgraph of G, and the E prime here is the union of all the maximum matchings in G, and the second part is just everything else. For example, in this transaction graph on the right, the red edges are all the edges in core G. Now, a graph-based de-anonymization attack is simply to rule out the edges that are not in core G, which are also the edges that cannot correspond to a true sign-and-signature assignment. For example, on the right, we see that the edges 1, 3, and 2, 3, they are not in core G, and therefore we conclude that user 3 must have been the real signer of ring 3. From this, we can see that if G does not equal to core G, then some users will have decreased anonymity in the sense that their effective ring size is reduced. Our first result is on relating the security game that we just introduced and core G. For this, consider the trivial attack, where the adversary de-anonymizes a signer by random guessing, with winning probability being equal to 1 over k plus 1, and k here is the number of decoys. We proved that this trivial attack is optimal when using the partitioning samplers and G equals core G, in the sense that the winning probability of the adversary is upper bounded by the probability of G not equal to core G plus the fraction 1 over k plus 1. In other words, if G must equal core G, then the adversary cannot do anything better than random guessing. With this inequality, to upper bound the adversary's winning probability, it remains to upper bound the probability of G not equal to core G. We achieved this by proving some relations about graphs and also proposing two conjectures, which I'm going to walk through next. First, we map the problem of a transaction graph to that of a directed graph. Given a transaction graph G, we define the induced directed graph of G and is denoted by ID of G here. The induced directed graph has the same edges as the original graph G, but with the edges being reinterpreted as directed edges and the self-edges are removed. On the right, I'm showing an example of a transaction graph and its induced directed graph. And then, based on some results in the graph theory literature, we proved that first, the probability of G not equal to core G is the greatest when the number of users equals the number of rings, and second, this probability is upper bounded by the probability that the induced directed graph of G is not strongly connected. And therefore, from here on, our problem becomes to upbound this probability that the induced directed graph is not strongly connected. Now consider the induced directed graph of a partitioning sampler. Recall that a partitioning sampler would sample some k decoys uniformly randomly within a chunk. We observe that in the induced directed graph of a chunk, each of the nodes has in degree k, and the k incoming nodes are sampled uniformly randomly from the other nodes. In the literature of random graph theory, graphs with this type of randomness is called the k in degree regular random directed graphs, and is denoted by curly G reg here. And therefore now we ask, what is the probability that this type of random directed graph is strongly connected? Unfortunately, this problem seems to be quite hard and has been opened in the math literature for over 40 years already, and we were also unable to solve it. To circumvent this issue, we turn our eye to another type of random directed graph called the binomial random directed graphs, and is denoted by curly G being here. In this type of random graph, each of the possible directed edges would exist in the graph with some probability p independently. It's called binomial random graph because the in degree of each of the nodes here follows the binomial distribution. To relate the distributions G reg and G bin, we propose our first conjecture, which says that for fixed number of nodes n and the probability p being equal to this fraction shown here, the probability that a directed graph G is not strongly connected when sampled under Greg is upper bounded by that when sampled under Gbin. Although we couldn't formally prove this relation, we note that this is intuitively true, since for all graphs in the support of Greg, each node must be weakly connected to k other nodes, while this is not the case for graphs in the support of Gbin. We also conducted empirical experiment, and the result shows that this conjecture holds for all graph size greater than or equal to 16 and for all values of k's tested. Taking this conjecture, now our task is to look for an upper bound for this probability that G is not strongly connected when sampled under Gbin. For this, we make use of an existing result on the limit of this probability when the graph size n tends to infinity. We tweaked the formula of this limit a bit and obtained our second conjecture shown here, which is a closed form upper bound for the probability that we want. Again, we conducted empirical experiment for this relation, and same as the previous one, this conjecture also holds for all graph size greater than or equal to 16 and for all values of k's tested. Now we can put everything together. Recall that we want to upper bound the probability of G not equal to core G. We related this to the strong connectivity of the induced directed graph of G, and for a partitioning sampler, the distribution of its induced directed graph follows the distribution of the regular random directed graphs. Then, using the two conjectures that we introduced, we obtained a closed form upper bound for our probability of interest. Finally, going back to our security game, which is also our global anonymity measure of ring samplers. We want to upper bound the winning probability of the adversary, and earlier on we had this relation here. If we set the probability of G not equal to core G to be at most this fraction here, then we see that a graph analyzing adversary is at most twice as successful as with the trivial attack. In order for this to hold, if we assume the two conjectures, then using our results, we can derive that it suffices to set the number of decoys k to satisfy this inequality here, which is just logarithmic in the total number of users. And we say that with this number k, it suffices to resist graph-based de-anonymization attacks. Here is a summary of this talk and also the link and a QR code to the ePrint of our work. Thank you very much.